Stationary data is really important when you want to build out time series models. So what we're going to be doing today is covering how you can identify stationary data with the help of ACF, PACF, as well as a few different hypothesis tests. And then we're going to jump into how to make data stationary if it is not already. And this is going to be covered through log transform as well as differencing. So a lot to cover today. Let's jump into some slides and then we'll jump into some Python coding. All right, let's jump right into it. So first, what is stationary time series data? Well, it presents no long-term trend or seasonality. This means that it has a constant mean throughout the time period, as well as constant variance. And the example of the graph over here to the right shows stationary data, right? You have like a horizontal line over here. We're not seeing any growth. We're not seeing any decline. And since it's a straight horizontal line, right, there's no seasonality associated with it, right? And the variance across the board is about the same. And one thing to note is this is not typically the case with real world data. So most real world data will either show some type of growth or decline, or it'll show some sort of seasonality. So one of our goals is to transform data into stationary when we want to work on models, right? And the reason why is it's the assumption on a lot of models out there is that our data is stationary. And the reason why we want to use stationary data is for models, it's easier to transfer what the model learns earlier on later data points, okay? So just a few different graph examples, right? So non-constant mean, you can see that this continues to grow over time, right? The opposite could be an effect if it kept going down. Non-constant variance, right? So you can see small variance, larger variance, even larger, and it continues to get larger. And then we have our stationary data over here. This one data point may look out of line, but it's stationary in comparison to all these over here. We'll also be going over a few different tests on how to actually know if our data is stationary or not through hypothesis testing, as well as taking a look at some charts. But we'll jump into that a little bit later. Okay, so this may be hard to see, and I apologize looking at this now, but I have 9 charts over here, right? And I want you to make the assumption of what is stationary or not based around these graphs. So maybe pause the video for a second, think about it, and then continue on. But I'll be moving forward to the next slide in a second, which shows the results. So pause now, then I'll move forward. So over here, 1 non-stationary, right, continues to grow. 2 non-stationary, right, grow down and then grows again. 3 non-stationary, you can see, continues to grow over time. 4, 5, and 6 are essentially stationary, and then also 7 over here, essentially stationary. 8 continues to grow. 9 grows, goes down all the way over here, so not stationary. So how can you turn your data stationary? Well, you can use a log transform, which impacts your variance. You can also work with differencing, which impacts the mean, and you can also combine steps 1 and 2, but you must use your log transform first and then difference also. There's another way to do this through Cox transform, and I'm going to be covering that in a separate video, so make sure to stay tuned for that. It'll probably be right after this in this series. Okay, so log transform stabilizes fluctuations by compressing larger values to relatively small one, works well with data exhibiting exponential growth or multiplicative seasonality, and helps make the variance more uniform. So this is just a before and after, right? So you can see before over here, we go from 60 to 180, right? Then we applied our log transform, and our data now goes to 4.2 to 5.2. And obviously this is not stationary yet, but it's a step in the right direction. And over here, I just wanted to show you that overlaid, these graphs are different. First time I built this out, just plotting it over here and putting on the slides, I'm like, man, this looks very close to each other, but they are actually not. This is the exact overlay right over here. And you can see that even closer on this side of things. Okay, now let's talk about differencing. So this is finding the difference between consecutive observations, and this eliminates linear trends within data. So here's our example over here of Apple closing prices, right, all over the place. And then we do take the differencing, and you have this result over here, which almost looks stationary. This would have to go through a test to determine if it is or not. But again, looks way better than our before over here, right? It has our constant mean. You can see here it's probably around 0. and the variance looks a little bit constant, although at the very end it does spike a little bit. You can see how when we start small, we get a little bit larger. So not 100% sure that this would be stationary or not, but I can't remember if we test that one or not in our Python code a little bit later, but stay tuned. Okay, so log transform and differencing. So you can actually combine both of these to make stationary data. So always log transform first before differencing. It's super important to do so. And you can see this example over here, right? Our before, and here is our after, right? From -8 to over here to the positive 0.08. And just to show you over here, like this went from -7.5 all the way to 10. So our data is compressed quite a bit, right? So how we can determine if our data is stationary through testing, our first example is going to be the ADF test. This is the most common one that you'll see out over here, right? The null hypothesis states that it's not stationary, and then also our alternative hypothesis says the data is going to be stationary. Typically, when I run hypothesis tests, I look at setting a significance level to 0.05. And so a small p-value suggests rejecting the null hypothesis, meaning this series is going to be stationary. The KPSS test, right, also can do this, but it's opposite null and alternative hypothesis. So for KPSS, the null hypothesis states it's stationary, alternative is not stationary. A bit confusing that these are opposites, but just go with it. So some code out there will just use the ADF test, some will use the KPSS, some will use both. We're going to use both in this video just as an introduction. Also, there will be separate videos just on ADF and KPSS in the future. I have not recorded those as of yet, but I do plan so for the series. Also, you can take a look at two different plots, the ACF plot as well as PACF. Those, we do have videos here on the channel already. The first ones we uploaded. But the ACF is the autocorrelation function plot. And what this does is it displays the correlation between the time series and its own past values, which are the lags, right? So the x-axis represents the lag, and then the y-axis shows the correlation coefficient anywhere from -1 to 1. So how you can interpret this, right? If it has a gradual decay, it indicates non-stationary, right? There's some sort of trend in the data. You can see that over here that this is a small gradual decay. It keeps going down, but this means we do not have stationary data, right? Sharp cutoff indicates stationary data. And then with repeated peaks, right? That means there's some sort of seasonality in our data, and that means it is not stationary. So over here, right, this is not stationary. You can see the gradual decay, whereas the second graph over here, right, we have our 0 lag. And if that doesn't make sense, I have a full video on ACF, right? We start with 0. And then after that, everything is over here and it looks pretty good. All right, and now let's take a look at PACF. So PACF is the partial autocorrelation function. So this measures the correlation between the series and its lags while controlling for the influence of intermediate lags. So how you can interpret this, a slowly decaying PACF plot may indicate the presence of seasonality in the data. So if it's slow, like the one over here, right? The top one I should mention. I don't know why I just pointed my screen. There's some sort of seasonality associated with it. And also, if the PACF does not show a clear cutoff, it might suggest that the data is not stationary still. So you want to be able to use your log transform as well as differencing or boxcox to make stationary data. Again, full video on PACF on the channel. I'm not going to cover all the nuances within this video. So, all right, we covered quite a bit, right? Two hypothesis tests. We covered also ACF, PACF, as well as how we can make our data stationary. So what I want to do now is jump into some example Python code. We'll go line by line, and then we'll take a look at more stationary data. All right, so let's get started. What I did first is I dropped in this all stocks 5-year CSV. It's a data set I grabbed from Kaggle. I'll put the link down below in the description, or you can search it and use it from there. First thing we're gonna have to do, we're gonna have to bring in pandas. So go over here, import pandas as PD, then import numpy as np, then import matplotlib.pyplot as plt, from stats models.tsa.stat tools, import KPSS and their add fuller, which is our ADF, and then from stats models.graphics.tsa plots, import plot ACF and plot PACF. All right, that's what we'll need. And let's get going. So what we're going to do is set up a data frame. So just to show you what this looks like. So we'll say df equals pd.read CSV. Then what you want to do is go over here and grab the link to this file. If you are not using Colab, just grab the path on your computer. Also make sure single quotes. And then I'll just go over here just to show you really quick. We won't be using all the data. We're just going to use one stock. So we use Apple, but you can see date, open, high, low, close, volume, and then the name. So, all right, what we're going to do now is specifically look at Apple. You can use whatever company you want, but in this series, I've been using Apple. I don't know why, but just decided to go with it. So company AAPL over here, and then we'll say company data. This is in the way, but company data equals, and we'll go df name. We're going to say equals company, and then we're going to create a copy. So copy, that's great. Then up next, we're going to say company data date equals pd.to date time, company data, and then pass in date over here also. Right. And then what we have to do now is set our index. So company data.set index, pass in date, and we'll say in place equals true, place equals true. Then what we're going to do next is just plot our data. So we'll say plt.figure, we'll set our fig size. So fig size equals 8.6. Okay, plt.plot over here. I'm passing company data. We're going to get the close value. So close. We'll say label equals original time series. God, my spelling's terrible. Original time series. This should be data, not date. All right. Next, what we're going to do is set our title. So plt title, Apple closing prices, plt.x label, dates, plt.y label, closing price, plt.legend, plt.show. I know it's a bit tedious. Well, we're going to probably reuse bits of this a little bit later when we do some other graphs, but here is our first plot. Okay. So what we're going to look at first is a log transform. We'll start off with that. Say log transform. And all we'll do on that is we'll go to company data. We'll go over here and say log close. So log close. And we're just going to go to NumPy. So NumPy, so np.log, and then pass in our company data. So company data, then passing close over here. So close like that. Right. And then what we're going to do, as I mentioned, is good old copy and paste. So grab all that. We're just going to plot this out. We're just going to put log close here, and then we'll say log time series, Apple closing. That's fine. So you can see now that our values are from 4 to 5.2, where over here it was 60 to 180. So we've compressed our data. It's not stationary yet. So what we're going to do next is take a look at differencing. So we'll go over here at differencing. And all you have to do for that, we'll go over here to say company data. We'll call it diff close. And we're going to say that equals to company data close dot diff. So diff like that. Right. And good old copy and paste. So grab all of this over here, and then we'll say diff time series. And now you can see, right, they're closing -7.5 to 7.5, and we're centered around 0 over here. Okay, awesome. And then what we're going to do is combine both of these together. So as I mentioned, right, you have to log first and then diff after. So what we're going to say is log transform with diff, right? And let's do that. So we'll say company data log diff close equals company data. We're going to grab our log close this time because we already did the logarithm, right? No need to do it again. But this time, after we do the logarithm, we're going to difference, right? So diff like that. And again, copy this code. And I'm just going to call it log diff like that. Log diff time series. Doesn't really matter. We're just plotting it. This isn't going into a presentation, but you can see like closing price, right? Now we have negative 0.8 to 0.8, which closing price is not technically accurate on here. We should probably relabel this. So like put it over here. We'll say difference log of closing price. And you could honestly do the same for these, right? Like just change them up if you want, but we're speeding through this tutorial. I just wanted to show you essentially what the graph looks like. But regardless, we go from negative 0.8 to 8, right? Our value over here is centered around 0. So this looks a lot better on the stationary side of things. So what I want to do also is take a look if that's accurate or not. One other thing I should mention is you do want to make sure that there are no null values from differencing. So it's pretty common to just do that. So just go to company data .drop NA and place equals true. Always just double check. And yeah, so what we're going to do now is take a look at some tests. So we're going to start off with ADF test. So we'll go over here to our ADF. All right, so we're going to look at the ADF test now. And probably the easiest way to do this is to write a function. So we'll go through that. And I will have a full video on ADF test on the channel shortly. So highly recommend you check that out, both ADF as well as KPSS. All right, so we're going to say def. We're going to put ADF over here. We'll say test, pass in our time series. All right. And then what we want to grab over here is result. So say result equals add Fuller. And then all we're going to do is pass in our series, right? And specifically here, we're just going to take a look at the p-value. So what I'm going to do over here is print out our p-value. So I'm going to use an f string, and we're going to say p-value. And in over here, we're going to grab our result. Great. And you're going to go result 1. That is where our p-value is located within the add Fuller test. It gives us a lot of data, so I'm only caring about the p-value in this instance. Again, we'll dive into ADF a lot more detail in that specific video if you want to learn more. Okay, so now what we should do is write an if-else statement. So we'll say if result 1 is less than 0.05, 0.05, we're going to print out, and I'm going to just copy my code that I have over here. So I'm going to say print conclusion, the series is stationary, reject HO. Then we'll just do an else over here. And again, I'm just going to copy over what I've already written. And all I have to say is conclusion, the series is not stationary, fail to reject HO. Pretty easy function on this side of things. And then let's just run our ADF test. So what we can go over here is ADF test, right? And then all we have to do is pass in our company data. So company data, and this is just going to be the close. So close like that. And what we can find is we get our p-value, right? And then we already have our if-else. So it says the series is not stationary, right? Now let's run this on our next one, which is log transformed, right? Let's test that. So you can see we had a pretty high p-value here. Okay, and now let's try our log close. So I'm just going to go over here and do log close like that. And you can see our p-value did go down a little bit, but we're still not stationary. Now let's take a look at our diff close, right? So we'll go over here to diff close. And you can see our value on this is 0. It says it's stationary. And it should be the same for log diff close, right? Because we're just taking log transform. So we'll go over here is copy that. I believe it's just capital L-O-G, like that in front of it. It is not. Let's just grab that. Should have had probably proper capitalization. But you can see p-value close to 0. And the series is stationary on that side of things. So that's what this looks like, right? And what I want to do is now show you KPSS. So we'll go over here and essentially do the same thing. So we'll grab this, right? And we'll call this the KPSS. So just say KPSS, right? And this time, what we'll say is the series is not stationary. Not stationary. The series is stationary. So what's a little confusing is these are flipped between KPSS as well as ADF, right? So under KPSS, right, if our result is less than 0.05, it is not stationary, right? Otherwise, the series is stationary. So think of it as the reverse. We have to change this up over here too. So instead of add Fuller, just put KPSS. So result equals KPSS, pass in the series, print our p-value. So this should be fine over here. And then we can do the same thing all over again, right? And we go over here. And this time we just say our KPSS test. And what I'll do really quick is copy all 4 of these. So just to show you how that works. 2, 3, as well as 4. And then we'll just copy this KPSS test for each of these. A lot of copying and pasting, but regardless, right? KPSS test over here, right? It says p-value 0.01. Conclusion, the series is not stationary, reject HO, right? Which we already knew that. Over here, right? Same p-value 0.01. This series is not stationary. And also, I should mention, right, it says the test statistic is outside the range of p-values available, and the lookup table, the actual p-value, is smaller than the p-value returned. And that's fine because we're already rejecting it, right? Then I run this again, right? And says the series is stationary, fail to reject HO. Then we also get the actual p-value is greater than the p-value returned. Again, that's fine since we're looking at 0.05. And lastly, over here, again, we get a p-value over 0.1, and the actual p-value is greater than the p-value returned. All right, and lastly, what I want to do is plot the ACF as well as the PACF. So we'll plot 8 different graphs. We'll plot both ACF and PACF for these data points. So we'll say close, log close, diff close, as well as log diff close. We'll just build it in one altogether. So let's go ahead and do that. So we'll say over here is fig axes equals plt dot subplots 4 and 2. So 4, 2, fig size equals 1014, right? Then we'll say plot ACF. We'll go over here and say company data close. Here, x equals axes 0, 0, 0, 0. Then over here, title equals ACF original. Then what I'll do is copy all of this, and we'll do this for the PACF. So plot PACF, company there, 0, 1, and then PACF. So what I'm going to do is just copy this over and over for each of the others, right? And we'll just leave a little bit of room. We'll change this out as well. There's that. There's that. So the first thing we'll want to do is change these up. So over here, this will be 1. So 1, 1. This will be 2. So 2, 2. And this will be 3, 3, and 3. Next, what we'll do is grab our log close. We'll change that for these. Then we'll go up over here, grab our diff close. And lastly, log diff close. Great. And then we'll just go over here, ACF. And instead of original, let's remove that for each of these down over here and give a little bit more context. So I'll say log close like that. Just copy that. And I'll copy this here too, is we're just going to say log diff close. And then we'll just say diff close. And that should be fine. Again, this is just for YouTube video. We're not presenting really anything to stakeholders, so nothing really too special. And then we'll go over here to plt.titleAunt, right? Layout like that. And then just plt.show at the very end, plt.show. And all right, great. Now let's run this over here. And what you'll see is we've now plotted the ACF and PACF for each of these across the board. And again, there's a lot more modifications that we can make with these also. I detailed that in both of the videos for ACF as well as PACF, and I detailed how you could specifically read these, right? What you can see right out the bat as this slowly descends, right, which tells me right away that our time series is not stationary, right? And you can see the same thing for over here for the log close. But what's good is like once you go over here, you have 1, and then everything is contained over here within this boundary. Essentially, this looks like it might be out, and that's just because of these dot sizes. I changed those up in another video, right? This is just some quick code, but and you can also see that this tails off really fast after the first one, which is something we also want to see. And yeah, so ideally, right, these two are going to be stationary. And also just to show you like how these line up, we talked about the first two not being stationary because of these ACFs, right? Well, both KPSS as well as ADF showed us that, right? Our third and fourth graphs over here, right? These both show stationary for the ACF as well as the PACF, and those hypothesis tests also proved that for us, right? We took a look at the p-values, and it showed us that, you know, this is stationary, and also just analyzing these graphs, you could tell right away that these are stationary. They don't have any seasonality associated with it, and it looks really good. But really the easiest way is if you take a look at ACF, it slowly goes down over here, or you see some type of seasonality associated with these. It's not stationary, but regardless, full videos covering that and much more if you want to learn that. This isn't going to cover ACF and PACF, but ideally that is the code for this video. We did cover quite a bit, right? I'm just plotting this, showing you the log transform, showing you differencing, as well as log transform and differencing. Then we took a look at ADF, KPSS, and then quickly just plotted both ACF and PACF. Those are the steps I would highly recommend you take a look at. And also, we do have another video too on the Box-Cox transform. That'll be a little bit later. A lot of the concepts will be applicable to that too. So yeah, that's it. Hey guys, thanks for checking out this video, and hopefully you're able to learn something new or clear a concept that was confusing. If you did, make sure to subscribe to the channel. We're uploading anywhere from 2 to 3 different data science focused videos every single week. And listen, if you want to continue learning about time series analysis, well, I have a few videos linked down below in the description, or you can click on this playlist that I'm currently developing right